Hey everyone, welcome back. Um, yeah, okay, so we're talking about moving to the third of the four models, getting more physical with the models, less idealized of these models of trapping. We're working with a Galton-Watson tree, and its characteristics are to be supercritical. That means that the mean number of offspring exceeds one, and there's a positive probability that the tree is infinite and doesn't die out. That accompanied by the other characteristic of having barren vertices. So in the offspring reproduction law, P of 0 is actually positive. So we have leaves, and therefore we have traps. Yeah, so this kind of situation, there's a clear division into a backbone, a collection of vertices which have a infinite forward going path to infinity, and the remaining vertices which are partitioned into traps. So each trap has an entrance at one remove from a location called the head on the backbone, and the entrance is the head, or is the top of a finite descendant tree, which is a trap. So those are the connected components of the complement of the backbone. That's the backbone. We have the moment generating function of the offspring law, call that F, and you have this picture with the slope that's greater than 1 at 1 and a positive value at 0. So you have a unique value strictly between 0 and 1, at which you have a fixed point for F. That is called, I'll call it R. That is the extinction probability, the probability that the tree begun with a single individual, the root dies out. Okay, so just recapping here these definitions, you have this nice Harris decomposition rarely that can be seen as zooming in on these two subsquares in this picture and having new moment generating functions. H on the left is a subcritical object, and G on the right is a supercritical one, with the difference that there are now no barren vertices for G. So that's the backbone moment generating function G, and H is the finite trap moment generating function. So the Harris decomposition involves drawing the backbone according to the offspring law corresponding to G. There's a little bit of fiddling to do with trap entrances that have to be, you have to figure out the exact law, but having put them in at one remove from the backbone, the actual laws of the traps are simple to generate. They're just independent samples of the trap law, which is pH to the subcritical H. So that will be our environment on which we work. We naturally condition on the positive probability event of having an infinite tree. That will then be our backbone. That will then be our environment, rather. Yeah, and as for the actual law of the walk, well, in the first instance, the obvious thing to do to adapt and develop from our previous model is to take a bias beta that can be bigger than, well, it doesn't actually have to be bigger than 1, in fact, because, yeah, well, okay, the bias beta is a number that can simply be bigger than 0. And then you have this rule, right? Any given location, there's a unique way back to the root, and then everywhere else it leads away from the root. So these are the weights. The reason that you wouldn't necessarily have to have a bias bigger than 1 in order to be sort of drifting away from the root is that the actual geometry of the tree may, unlike in the co-model, the actual geometry of the tree may favor forward roots. Yeah. So
Can I ask one question about the tree again? I think this is just articulating a question I tried to ask last time that I didn't understand. So it's clear that like for every non-leaf node, at least one of its, at least one of the subtrees rooted at its children has to be infinite. Otherwise the tree would be finite. But is it true that exactly one of them is infinite? Or could you be in a situation where there's a backbone, but then one of the traps is not large, but actually infinite?
the traps can never be infinite. I don't know whether I completely agree with the statement that every non-leaf, say that again, every non-leaf.
Oh, if you look at a non-leaf node, then you can look at all the subtrees rooted at each of its children. And at least one of those has to be an infinite subtree. But I'm curious if exactly one of them has to be infinite.
No, the backbone is not a one-dimensional structure. It has several routes to infinity. It shouldn't be a name that misleads, or the work we did in the previous case shouldn't mislead. That you can definitely have several routes to infinity. Basically,
I see. Okay.
If you're actively sampling the system, let's say without any conditioning whatsoever, then I mean any given vertex you get to, when you look to the future from there, you have this probability of, I think, 1 minus r bigger than 0, that you're infinite. So that necessarily means if you have, say, 3 children, they could all have that property themselves. So you can definitely have this sense of a backbone with different possibilities.
I see.
Every trap is definitely, though, a trap can be a trivial thing. So if this is the backbone, this is actually on the trap, the head, and then this is the actual entrance to the trap. But the structure here could be completely empty. It could be the entrance is the beginning of a trivial trap. But any trap here, it's sampled according to pH. So it's definitely a finite structure.
I see.
Okay.
Okay. So there's something somewhat surprising, at least, which is like that conditioning this tree on being infinite, like, still makes the distributions at each node have some independence.
Yes, but the view is, I think, that you condition it to be infinite, and then the first thing you draw in the Harris decomposition, in some sense, is the infinite piece.
I see.
There's this structure where you have forward routes to infinity. So in some sense, that takes care of the need to be infinite. So then what you draw on top of that is, in a sense, the things that weren't so successful. You draw out the entrances in a way that I haven't been completely explicit about. But then from then on, actually, it's just by definition at that point, you've already drawn the infinite structure. So what remains are the finite pieces. So in that sense, it's quite natural that you have independence, because none of these pieces are interacting with one another. The need to be infinite has been kind of taken care of. These are all independent finite traps.
I see. Okay, cool.
And they're fairly small. I mean, you see in the previous model, speaking of trap depth, it was just by fiat that we said that the trap depth would have an exponential distribution. Here it's actually a physical problem. So if we have a trap, when we sample pH, the outcome sample, I'll call it T, that's the tree, and then that tree has a depth, dt. So what's the depth? It's the natural thing, right? It's the maximum. It's the number of generations it survives. So any tree, the root is a generation 0, and so this, for example, has depth 3. I won't. It's somewhat obvious what the definition is, right? It's the maximal index such that the generation is non-empty. So in this case, there are great-grandchildren, but nothing beyond that. So the depth is 3. So the depth is a nice random variable then defined under the finite law, the trap law. So we presumably want to understand this quantity. What is this quantity, or anyway, what are the fundamentals of how it behaves when k is large? Okay, well, all right, does anyone want to shout out at more or less high level of detail what the answer should be, or what you believe the answer is? Well, okay. I'm going to give the answer in fairly precise terms, but the answer is exponentially decaying in k. The intuition for that is kind of that we've already conditioned the object to be finite, but for an underlying object that has a zest for infinity. Every every child that gets born in the structure wants to reach out to infinity and has the capacity to do that in an unbiased way, which is somehow positive. But we're actually working under a constraint and a conditioning that that's not happening. So somehow there's a sense that every new individual you put into the system, there's a positive probability in the unbiased sense that they go to infinity, and that's not happening. So you're sort of, by Bayes' theorem, somehow you're sort of crushing those down, and you don't really want to have to deal with it. So there's an exponential tail. But what I actually want to do to try to convince you of how this behaves is to consider the iterate. I'll use a notation like this. I suppose it's always a question when you talk about iterating a function, how you distinguish from multiplying the function. So I don't really remember what people do, but I'm just putting this bracket around n. I mean, of course, the iterate of the moment generating function, n times. So h of 1 is 1, of course. So it's h, and so on. So that has a very particular interpretation for the, does anyone remember what is hn in terms of its status in terms of trees and what's it called, branching process theory? It's, I believe it's the moment generating function of the population at stage n, at generation n. So, well, I'll just write the formula for this. Okay, so if I write it in terms of a power series, this object here is the probability that generation n contains I individuals. You can see this, it's a bit heavy-handed, maybe there's a more conceptual way to do it, but you can prove this by induction. Let me just take you through the first step. What's h2 of x? It's the iterate of h with itself. So that is, of course, in terms of the power series, hi, this variable, it's h of x raised to the power of I. Yeah, okay, so then I have to write out the power series for h again. Let me introduce a variable j in order to do so. Okay, we've got these kinds of expressions. So now I want to sort of expand out and gather terms to try to identify what the coefficient of x to the j is in the, I need quite a big line for this, so I'll go onto a new screen. You know, I'm gathering terms basically. What's the coefficient of x to the j? So I have to toggle between screens here. Well, yes, okay. So the first thing I'm going to do is select the value of I in this screen, but for some reason I relabeled it as K. I think that's what I'm doing anyway. It could go up to infinity in principle. HK. So what I'm doing, I think, is I'm choosing as far as the language of this screen is concerned, I'm choosing a value I that's greater than or equal to 1. And then what I'm doing is I'm taking that product you see, the i's power, and then I'm having to have a situation where the various xj's that contribute, they have to add up those j values to k in order to make a contribution over here. So there's various ways that can happen. I'm summing the k different indices I have. They have to add up to, did I say it correctly? Anyway, they have to add up to j. And then each one of these comes with a product weight which is H at JL. So it's a bit of a mouthful, but it has a simple interpretation. It's that we have K children in the first instance. We're interested in what's going on. The claim is this is to do with generation 2. So what's happening to get the contribution is that at generation 1, the root of the whole system has K children. So they're sitting there at generation 1, and then they have to collectively contribute J children. So what happens is that the first child has J1 children. The second has J2, and so on. So the final one, the kth, has JK children. So you see, by imposing the constraint that those grandchildren numbers add up to J, that's the population size at the second generation. And so that's the various different routes, disjoint routes you can have to obtaining J children in generation 2. Yeah, so then that inductively, you can induct that to obtain what I said, which I didn't label, but I'm referring to this statement. Okay, so that means that we can do some computations about this. We can compute the mean number of children in generation n on this basis. Let's call that mn. So this is the mean population size in generation n. That's given by the HNI was just my definition for the probability that generation n has I children. So that's an expression for the mean population size in generation n. So that is going to be the derivative at 1 of the moment generating function for that population, which we've just identified to be the nth iterate of of H. And then it's easy to compute this because it's the chain rule done iteratively, but it has a very simple form. I'm always putting this derivative outside and then considering these kinds of expressions. This is an iteration of the chain rule. To obtain this type of expression, there's n terms in total in the product, and they're all being evaluated when x is 1. So h of 1 is 1, and h of any iterate of h is 1 at 1. So this expression is simply the nth power of h1 prime, which is, if you recall the relationship between h and f, well, the relationship is that h of x is equal to frx divided by r, where r is the extinction probability. It's the x coordinate of that little square right-hand side. So that means when you do the chain rule that h prime of 1 is f prime of r. Okay, so this is a formula for the mean population size at generation n, and as we expect, f prime of 1 is less than 1, right? I won't draw it, but that picture, when it's going through that corner, that point in the middle at an angle that is less than 45 degrees with the horizontal at that stage. So that's less than 1, reflecting exponential decay in the mean population size. So what's going on is, if you look at a sample of a deep, this is going to be a deep trap. So if I take pH sampled with high depth, conditioned on the depth being bigger than some large values, then you will have a couple of offshoots now and again, but the intuition and the heuristic is that the picture will look like this. Because you see, every time you do an offshoot, you have to kind of manually kill it off. Each one of these offshoots dreams of infinity and has to be nipped in the bud with a positive probability. So this is not going to be a structure like a backbone with several competing large roots. Every one of those roots will have a tendency to flourish and need to be sort of manually killed off. So it's going to remain a rather rigid one-dimensional structure with relatively few offshoots. So what that points towards, and here I'm drifting rather into intuition to some extent, I'm not going to carefully justify this, that the event, the probability that generation n is non-empty, that there's actually somebody who survived to depth n, i.e. that the depth exceeds n, this is, just understand this to mean up to a constant factor. Okay, this is actually behaving in the same way as the mean, the mean size of generation n, which is what we've just been computing. Because you see, obviously if generation n is empty, then there's no contribution to the mean size. But if generation n is non-empty, the view is that it's very much a bounded number of individuals who survive in generation n when it is non-empty. It's 1, 2, 3 individuals typically, not many. It's specifically something that remains bounded independently of n. That's the intuition I'm hoping to work with. And so we've computed this right-hand side just now. Okay, so this is a quasi-proof, as so many in this class. This is a approximate proof of the proposition about trap depth. And this is something that replaces the statement that was true by mere definition for the more idealized cone model, that the trap depth is behaving in this kind of way with the usual meaning for tilde. And the alpha is a constant I'm not going to compute, but it relates to things like what the mean trap depth, what the mean number of people in generation n is, given it's not empty. It's sort of something that's going to feed into that constant in some form. Okay, so we're seeing how the model we're working with is plausibly relatable to the cone model and to the even more idealized model before that. Okay, we're seeing similar statistics. So there's two directions I could take this. The one that's most direct and natural is a constant bias model. This was studied with Gerard Benarous and Alex Freiberg and Nina Gantert, as well as me. And then the other one I'll mention, the random bias, was studied by Gerard and me, Gerard Benarous and me. So, okay, well, I can tell you briefly what they both are. So it's very natural what the first one is. It's just basically back towards the roots or out towards infinity in the other directions, however many there are. These are the weights. So here beta is a parameter between 0 and infinity. So the overall parameters of the model, of course, are the PI sequence that specifies the offspring distribution at large and this parameter beta. So yeah, okay. Now, all right, if you believe that, roughly speaking, we're going to get into the game plan of the idealized models, then we have this sense of concentration of sojourn in traps around powers of beta. So I attempted to indicate, I don't know how successful I was, that there is this impediment to convergence to a random double staircase under scaling, particularly if beta is very high in that case. So that raises the question of, can the structure of the problem nonetheless be analyzed? What sort of random double staircases occur under subsequences of scaling, and there's a sense of a exponential, well, there's a certain periodicity about that. So I could tell you a bit about that, I suppose. The other thing you can do is, if you buy that there's an impediment to that kind of convergence, what can you do to change the model in order to assure convergence? So let me at least begin saying something in that direction, because it specifies the other main route for this tree discussion. So this is, as I say, the work with Girard. So here we could randomize bias. I mean, suppose that for now they're just given that to every edge in the system there is a bias beta E, but now it depends on the edge. So this is the bias you use when you consider moving along the edge away from the root. The root is back up here, higher up in the system. And so if you're back towards that root, it's with weight 1, but insofar as you're moving in the other direction, it's going to be with weight beta E of the edge in question, okay? So then that raises the question, can we make an assignation of biases in a way that will ensure that we have, in some sense, more regularity in the system for the trap sojourn times that will permit a kind of random devil staircase picture to emerge without having to think about different subsequences. Yeah, so that's what we do with a non-lattice condition. So maybe I'll attempt to summarize this direction now. So, okay, so there's going to be anyway a law nu. It will be a law on, well, on the positive reals, but in fact on a compact subset thereof. As I stare at it now, actually, I'm not quite sure why we need to take the law to be entirely supported on values strictly bigger than 1. But anyway, that's the condition I work with. You know, from what I was saying earlier on, it's not perhaps entirely clear it's necessary for the bias away from the root to be always bigger than 1, because the actual geometry of the situation could create possibilities that mean that you anyway move away from the root without necessarily needing every single bias to be bigger than 1. But okay, that was the condition I work with. So it's actually going to carry a non-lattice assumption. This is the, you know, I mean, if I take the case where the law is a delta at beta, at a given value beta, that of course reduces to the constant bias case. What's needed to ensure a certain form of regularity for the time that's spent in traps is a non-lattice assumption. It's that the Z linear span of the set of points in the logarithm of the support of the measure is dense in R. So that will be the standing assumption for the random case. Yeah. Now, I'll just say I've got my notation. I think that's going to be hypothesis. It's going to be, in fact, hypothesis 2. There's another hypothesis. I'm saying them in the wrong order. I suppose that's why it's hypothesis 2. But okay. Yeah, so do you have a feel for that? The point is that you cannot have, say, flipping a coin with the bias being beta or a beta squared, you see. And if it's heads and tails, if that's the rule for determining for a particular edge what the bias will be, then that's the kind of thing that we are not allowing, because you see at the level of the support of the measure nu are these 2 points, and so the logarithm of the support are the values log beta and 2 log beta. And so the Z linear span of the logarithm of the support is Z log beta. And that's a lattice. You know, it's not a dense structure. And similarly, you know, obviously if I did other rational powers, that would also be a problem. And the reason that's not really getting us away from the kind of phenomenon that's causing the obstruction to the kinds of smoothness and regularity is that if you have this sort of sense of beta and beta squared, so if you have a trap of depth D, then there's a sense of maybe, well, anyway, sort of independent heads and tails decisions being taken. So you still get kind of the overall, the overall behavior is beta to an integer. So if beta is extreme, just think of beta as being really big, okay? So the time spent in a trap, is modeled by this kind of behavior. So, if you see an outcome like this, you know what the integer was, because the exponential is sometimes 0.1 and sometimes it's 2.1. But if beta is really big, then if I take the actual empirically observed time spent in the trap and I take its logarithm and then divide by log beta, in practice, if beta is really big, the integer is staring me in the face because it's integer plus log of an exponential random variable divided by log beta. So if the division by log beta is only for the error term. So if beta is big, you get numbers that are close to integers. So this continues to happen even if you have these perturbations of, if you have the lattice condition, you don't really escape this effect. So that's the reason that we do that. There's a very weak assumption. I'm slightly unsure actually what level of detail to, well, let me try. I suppose I'm going to mimic the introduction of the paper I wrote about this, the random bias case, which sort of tells you what the main results are, and then it has some tricks for explaining ideas without really getting into proofs. But it is precise at the level of the results. So I'm going to tell you at that level of detail what's happening. So I'm focusing here on the random bias case, leaving aside the question of what the precise theorem statements are about random double staircases for the constant bias cases. Yeah, okay. So the other basic input, the two basic inputs are the offspring law and then the random bias law. So we've stated the hypothesis for the random bias law. As for the reproduction law, it's what you expect. I've already said that we're supercritical but potentially barren at times. Okay. So then I just need a very weak condition. I'm certainly not going to explain how this condition is used, but in the interest of precision, I'll state it. It's on the tail. It's a very weak condition on the tail of the offspring law. It's not really going to be a significant point of focus. It's really these conditions that are fundamental and drive the physical reason that we actually have the phenomenon that we're finding are in the box there, okay, just being reiterated. So it's a bit of a mouthful. I'm going to give you the main theorem for this setup. So we're going to be seeing what, in essence, the random double staircase emerged, although it's not directly expressed in terms of that. Okay, so I'm assuming the two hypotheses. Okay, so the first question, I suppose, is what is the actual rate of progress? And well, what is the critical point somehow for zero speed? What characterizes trapping and zero speed? And then in the case where there is trapping, what is the sublinear rate of progress? So this is defined by an exponent gamma. So the condition is that the bias law is called a nu, okay? And then I do this integral. This integral can be performed for any positive gamma, of course, and there's a unique value of gamma for which you get this answer, So recall that R is the extinction probability. So, I mean, I don't expect it to be clear really why this precise formula is coming up, but some of the characters in the formula are familiar. We've seen f prime of R in its role in the trapped depth formula, the exponential decay rate for trapped depth. Anyway, that's just a definition of gamma, but gamma is an exponent that characterizes the zero speed regime. Oh, I should have said perhaps something about notation. Gamma less than 1 will be an important condition. Let me just put that on hold, or rather, let me expand something that perhaps should have been said as notation before we started. So there's a couple of aspects of notation in this slightly chunky expression. Okay, so what's notation here? An aside on notation. So this is notation for the decorated tree. So PF perhaps is notation, and I think it has been notation for the actual overall tree, which could be finite. I'll get to that in a minute. We then decorate the tree. Each little edge in the tree gets a bias, okay? And then obviously that determines the jump law for a walk. Now those biases are independently chosen according to the law. They're each distributed according to nu, and they're independently chosen. So that then gives what PF nu is. But then we want to condition that structure on the positive probability event of being infinite. And that's what this is. Okay, that's what that object is. So there's that's the environment side of things in the first coordinate there. This then is the actual the walk, which is just doing its stuff from the roots according to the rules that we specified. Okay, is that clear? So I think, isn't it true to say in this model there's 3 levels of randomness? There's the formation of the tree, PF. There is the assignation of random biases, stage 2 randomness, nu. And then there is the actual formation of the walk given that environment specified by the first 2 randomnesses. So there's actually 3 levels of randomness. Anyway, it's all there in that notation. So we then have our hitting time. I'm sort of building definitions into the theorem statement here. The hitting time for level n. This is the infimum of times t at which the walk is at distance. Oh, it's bad notation. This is actually the distance from the root. And t is perhaps a bad choice of notation. This is a discrete time process. So t is an integer. Okay, so that's the time, that's the first time that you've reached distance n from the root in the tree. So we can study that. So let's actually get to the theorem now. So Hn, remember the hypothesis that gamma is less than 1. This is intended to reflect a trapping regime. So 1 over gamma is bigger than 1. So this quantity is, I'm dividing Hn by something that is growing more quickly than n, reflecting the fact that we have a regime of sublinear progress, because this convergence in distribution I'm about to record is to a non-degenerate random variable of psi s gamma. Oh, well, okay. S gamma, this is a convergence in law. So, yes, this is, of course, as n tends to infinity. So there's these characters on the right-hand side. These are random objects it's a random object on the right-hand side. It's a random variable. So this is a classic object in this sort of random devil staircase world. I think I briefly mentioned it. That's what S, well, alpha could be any parameter, but obviously it's gamma in the actual application, but it's defined by this transform. This is anyway the one of these classic infinitely divisible objects that one tends to see in this theory. This is the stable law of index alpha. And then you have a constant sitting there that I'll get to in a minute, psi. Psi to the 1 over gamma, you see that in the limiting law. Perhaps we could also see it, perhaps it's arguably slightly preferable to see it at the level of where the walk actually is. So if we look at it under the same law, if we actually look at the distance from the root of the walk and divide it by n to the gamma, so that is a division by something that is, n to something less than 1, again reflecting sublinear progress. Here we have just a variation of this type of expression. So with the same random variable, which has the stable law of index gamma, playing the role of S gamma, we have this expression. This again is convergence and distribution in high n. And you can see the role of the constant psi is perhaps slightly clearer here. It's something that when it's large, it indicates a constant factor, that when it's large is actually tending to indicate a slowdown. So the kinds of things that we've seen various things happen that indicate these kind of correction terms are going to play a role. We've seen considerations of how having extra, you remember that discussion of the perturbed co-model where there might be a couple of competing leaves near the bottom of a trap that slow you down a bit. That would be something that you might expect to see represented in an expression for this constant psi, tending to increase psi and cause further slowdown. You have the possibility of going up to the top of a trap but coming back into it. That might be something we would expect to see somehow represented in psi. You have questions about backbone structure, because if you get to the top of a trap and then it happens around there, the backbone has some body to it and several different routes out to infinity, that would be something that would make it a little bit more likely that you would be able to make a clean getaway having escaped a trap. So that might decrease psi. So psi has a rather, it was not at this stage very informative, but it's more like a chart to keep track of things. It's a product of 6 terms. Yeah, so we have the Euler gamma function, which recall is given by this integral that's appearing in the latter 2 expressions. Yeah, all right. Well, then there's 4 other constants. It's a phi or a psi, isn't it? A psi, eta, d1, and d2. And I'm not going to say what they are at the moment. I think the view is to give you a kind of conceptual overview of what's going on in enough level of detail that I can at least tell you what these constants are and then kind of explain what their role is at a rough level in the kind of way I was just beginning to do in a sense. Now, okay, and then we should just say something if gamma is bigger than 1. Then that's a regime of we have ballistic motion. If gamma is bigger than 1, so then the time it takes to reach distance n is converging to a constant that's positive, and this is almost surely it's a given non-random positive constant with an almost sure convergence under this law with a slightly long name. This law, that's the law that governs everything. Yeah, okay, so I guess I'm gonna kind of follow the structure of the introduction I wrote to this paper that kind of signposts, a kind of detailed signposting for what's going on here without, there'll inevitably be a certain amount that might be a bit hard to remember about this, but I'll try to speak in a way that will indicate the main ideas. You know, one of the themes is that the the constant psi has these 4 unexplained constants at the moment. And, if I speak at a level of detail that at least indicates how they crop up, then, the idea is that you'll be able to have hopefully a rough sense of what's going on, indexed by some understanding of the role of each one of these. So, yeah, okay. So one view is that...
Sorry, Alan.
Yeah.
Can you remind me what xn was? I forgot.
Xn is the actual walk. It's just a walk. So
the walk on the tree. Okay.
It begins at the roots.
Okay.
And at each moment it takes these decisions, and we measure its distance. This is its distance from the root.
Okay. Okay, thanks.
Yeah. So, in studying these problems in a trapping regime, the picture to bear in mind is that we expect on a lengthy time scale, the physics of the situation and the behavior of the walk is going to be dictated by its falling into several big traps that will kind of dominate the time scale and will be the plateau in the random devil staircase. So these traps will be well separated from one another, in some sense effectively independent, and they'll in some sense be a tremendous distance from the root, because if we're studying a long time scale, we'll be able to, on that time scale, get a long way from the root before we find the deepest traps for that time scale that really dictate the outcome. So what that means is it's kind of tempting to view things from the perspective of entering one of the important traps at late time. So we have this kind of picture, an entrance with a trap lying below it as before. And then we will have this kind of outside. The inside is the trap and the outside is the environment viewed from, the view is to imagine that you keep track from the very beginning of time, beginning at the origin, beginning at the root. You kind of know every time you enter a trap, you reach the entrance of a trap. And suppose that you have a bit of a think about what it's like when you reach the millionth trap, and then you have a look around you. What do you expect to see? So you're at the entrance to a trap. So you're one remove from the backbone. So you can look to the outside, and you're kind of at a new origin at this entrance. And as you look to the outside, you see a fragment of a backbone, and that stretches back a long, long way towards the root that you left far behind you. And then as you look inside, you see a trap. So what you have is really a measure, I'll call it Q, that basically represents that. So this is the limiting environment viewed from the particle on the occasion of the particle's arrival at a new trap entrance after many trap entrances have been encountered. So what I was saying about sort of arriving at the billionth trap, what does it look like? So it's got a trap. As you look inside, you haven't really seen inside yet. So first arrival at a new trap. So you have an unpolluted trap in front of you with a rather a small trap, usually, because it's an exponentially decaying law for trap depth. But then what you might expect on the outside is you have a kind of convergence for the structure of the backbone. There's a kind of a limit in law for what the limiting view of this structure is, because it's somehow you've been moving along it in a linear fashion that creates opportunities for certain forms of independence and renewal to occur. So there's a sense perhaps of settling down to a statistical limit in law for what the outside looks like. So this is what the measure looks like. Now it's important to understand that this is a slightly different object to what we're working with, because the root actually makes no appearance whatsoever in this picture. The point is that in this limiting picture, the root has receded infinitely far. When you're moving along the backbone, you do so at a linear progression. So this is actually an object where it's a kind of it can be called a backbone tree pair in terms of the actual deterministic object that we're sampling. And in that object, there's a sense of the root's back here, but it's at infinity. So it's more like the actual backbone is now a slightly different kind of object. It's a tree, but it's a tree with one end distinguished that runs backwards in time to a root that you never reach, because it's a limiting picture. So yeah, okay, that's kind of what's going on. So the view is then we just are going to be studying. We're very interested. It's a bit like in the Cohen model. Very interested in the notion that we've just arrived at a new trap and looking to the future and thinking about the statistics for the outcome. That's very much the perspective of this law that I'm writing down. So. Well, there's a bit of notation here. The point is that Q specifies the environment, including all of, it's called a backbone tree pair. That's kind of what this notation is. And it has its biases. But these are all just being selected according to Q. So the random selection of the environment then dictates at that stage the form of the environment as a tree, and all the biases assigned are given data, and that's just what's being recorded in the walk randomness, which is in the right-hand term here. So that's the measure we want to work with. And then perhaps the single statistic of greatest interest is tau, the total time to be spent. I use the future tense or suggest it because, you know, the view is that we've just arrived at that trap, and we have this awareness of what we sample the environment and indeed the trap, and then we think, well, what time do we expect to spend in it? What is the statistics of that? The total time to be spent in the trap. So, all right, I have a theorem, the second main theorem, and really the first theorem is ultimately, well, the whole thing was rather involved, but I mean, at the end of the day, the second theorem is conceptually a fairly simple consequence of this. So, you know, I'm going to be writing all this notation. You may not be able to remember it all. What I'll try to do verbally is sort of constantly recall the meaning of objects somehow, so that I'm hoping to keep you on board with a rough sense of what's going on. So as I say, you know, think about that billionth step. We were keeping track from the very beginning of arrival at trap entrance, and here's a new one, here's a new one. Wait until you reach the billionth one and have a look at your world around you on the outside and the inside, and then begin to sample the walk in front of you. That is what this random object is, okay? What's the probability that for the trap that you're sitting at the entrance of, you're going to keep track of the total time you spend there? What's the probability that that's large, that that's bigger than X? So this is behaving like X to the minus gamma for the gamma that we've identified. And then I have, well, these mysterious characters, we've seen them before just in the statement of the previous result. They remain to be explained. But you can probably imagine that some of the considerations we've spoken of about, you know, gamma is going to be related to the basic probability of having a deep trap according to the law that we've found. Indeed, gamma is the exponent that appeared there. That's not completely true, but it's related to that. And then these corrections will be connected to things, like I say, about the structure of the bottom of the trap and things up at the top that relate to whether one has a tendency to fall back into the trap or not, having left it once. Yeah, okay, well, let me, I'm gonna, all right, it's a good time for questions. Do people at least understand roughly this statement, what this law is, and I suppose that's the main thing to ask. Do you have any questions about that? I mean, obviously at some level it's not clear. I haven't explained these constants and so on, but accepting that point perhaps, is this statement kind of interpretable? I'll assume yes, unless I hear, but I obviously welcome queries. Okay, so you know, I'm going to give you kind of some sort of tour of principal ideas and explanations that are leading to the two theorems. I'm certainly not giving proofs, or certainly not full proofs, not really any proofs, but I think some meaningful ideas. So the discussion we had before is relevant. We are revisiting to some extent the co-model. We have the commute time formula for the, you know, one basic question is the mean return time. So if we're at the entrance of a trap and we're thinking about going back to the backbone, how long are we going to spend in the trap that lies beneath us? Back down to the base of the trap, okay? So we adapt a definition that we made before. For every vertex for every vertex V in this trap, I can define an omega value that's somehow rooted at the entrance. It's the product of the beta E's on the route from the entrance to V. So, I mean, here I have E and E prime, those are the intervening edges. And each of these edges is decorated with a bias, okay? So in this particular case, the value of this quantity I'm defining is beta E times beta of E prime. And then obviously, in general, the number of terms is the length of the route between the two locations. So that's a definition that's made for every vertex V in the tree. This whole tree is a descendant, it's the trap, and it's the descendant tree of the entrance. So notation can be T ends. So I then define with this notation that emphasizes the sense in which the entrance is the root of the trap. I can define this to be, so yes, this is the descendant tree, this is the trap, T ends, but this quantity is simply the sum over all the concerned vertices in the trap of these values that I just defined. So it's analogous to, it's an extension of, it's generalization of the definition we saw before. In the previous case, beta to the distance was the, or that would be the formula in the constant bias case, but now we take the product of the weights, whatever they are, the beta values, whatever they are. So then we have the same commute time formula, which I think I certainly didn't explain, but I think Yang will give a talk in which we see the proof of the formula later on. The commute time formula. So how long does it take to get from the entrance of this tree back up to the head? So with the hopefully more or less obvious definitions, you know, just how long does it take in mean? It's twice this. I think it's in the electrical theory, it's called perhaps a total conductance. The quantity anyway, just defined. Okay, that sum is appearing in this role. And there's a -1. As I say, the -1 is its commute time. So the time to get out on the outward journey from head to entrance is 1. You immediately go there somehow. That's the reason for the -1 appearing. So, okay, if we're talking about, if we're mimicking perhaps previous discussion, one basic question was to talk about the mean time spent in a trap. Well, that's what we're talking about here. So this speaks to the question of how does omega n Tn behave? So yeah, let's move on to a new page for this. So trap, weight, tail. Well, weight, okay. Weight is a word I suppose I've introduced just now. I suppose maybe it's because of the omega notation, it's a bit like W. Anyway, the mean time spent in the trap is basically this omega statistic. So we want to study it, right? So we have, well, at this level, it could be any subcritical law. Obviously, we're interested in the one that's spat out at us by our choice of the PI sequence. We certainly have in the application these conditions of exponential decay on a subcritical law. So then we have nu, a random bias, that satisfies the hypothesis 2. That's just the basic hypothesis for that of non-lattice logarithmic condition, in essence. So then there's a proposition that says, this can be called proposition TWT. I don't know how often I'll refer to it, trap, weight, tail. Trap, weight, tail proposition. So what you see, what I'm doing, I'm very much interested in studying the statistics of a visit to an individual trap in the meantime. So this is the relevant law, right? I'm sampling the subcritical trap, pH, and then decorating it in the usual way with its biases. Okay, that's the notation for that. So what's the, yeah, so this omega t is, well, yes, it's exactly what we're talking about. So the view is that maybe in this notation, the root is the entrance. And so T is the entire tree. So it's exactly the formula we've just been seeing. The sum, you know, for this vertex, it's this times this, beta E and beta E prime being summed up. Okay, just the object we just basically defined before. The probability that this is bigger than U is behaving like, so D1 is one of our 4 characters, mysterious characters. Yeah, all right, so gamma at least satisfies, gamma is being defined as before, but let me recall, gamma is the unique positive value that's specified by this consideration where MH here refers to the mean of the offspring law H. It's that quantity. But in applications, that is, this quantity here is, in the application, MH is F prime of R. So if you recall, gamma in the overall context was being defined by this formula. Now, then there's the question of D1. Now, I think so that I don't end up with too many formulas on screen that perhaps aren't very enlightening unless we really take the time over this, and there is only so much time left in the class. I think I will not write the formula for D1, but conceptually D1, I suppose, telling you about, it's a correction that is due to behavior, I think, near the bottom of the trap. In a minute, I'll give you an explanation of why gamma is satisfying this formula. Yeah, let me maybe do that first, because then I can tell you why D1 is a correction. But it's a correction that's related to the notion that, you know, in the Combe model, this was somehow the trap, but now the trap has a little bit of structure and competition at the base, and that slows you down for your escape. If beta is very large, then this doubles and this triples collectively the time spent. So this is something that feeds into a formula for D1. So one would expect D1 to be some sort of sum over the base of the trap of competing vertices and some sort of mean expression involving that. Yeah, let me perhaps leave it at that. I'd quite like to tell you about the proof idea and to indicate why we're seeing this particular integral formula specifying what gamma is. So the proof idea, I suppose, is that omega t is, well, I want to say that things are dominated, like the picture I just drew. I have the view that the trap is a relatively sparse one-dimensional object with just a few competing little structures. Okay, this kind of view. So it's dominated by this type of expression. What am I doing here? I'm taking the view that the trap is really composed of a backbone with some other structures. So this is just focusing on the backbone, really. So what have I got here? This quantity is the depth of the trap. So in what is only a very slight idealization, it is geometric, and the probability that G is just the trap depth. So we justified this formula. For some constant I'm not going to bother to compute, I have this kind of expression, okay, that the more important constant MH is the mean number of children, which is less than 1. So we have this exponential decay, right? And then the BI, of course, are going to be independent samples of mu, reflecting the fact that they are simply the biases along the backbone. And then I have to multiply by a correction, which takes account of the neglect I have. Well, I suppose basically I just treated, what I did was I treated, if I didn't have the correction, then you see what I did was I basically said in the, at some level that this is roughly dominated by simply the base. Because then if you ignore the correction on screen, I've just written you the formula for the omega value at the base. But you have other contributions. You have a contribution coming directly from people higher up the backbone, and then you have a correction coming from the alternative tree structure and the other routes you can take, and particularly the ones near the base will be playing a role. But the correction will be a random factor, but with a rather fast decaying tail. We can think of it as kind of a effectively random but bounded factor. That will play into what D1 is. And I'm not really going to tell you what D1 is beyond this kind of motivation that indicates that the structure near the base of the trap should be very good at approximating this D1, which is, well, it will be a mean of a random but effectively bounded factor. So I'm more interested perhaps in just focusing on, as I say, this is, if I take logarithm here, then I'm dominated by the omega value of the base. That's what I want to study. And so in taking the logarithm, I have, with this slight idealization, is a geometric number of terms of a logarithm of beta I. And then there'd be the logarithm of the correction, but we're not working with that. So this plays into the defective renewal theorem, which is something that I'm not actually going to prove here. So I'm going to reduce the classical probability without, perhaps it will still unfortunately be in some regards slightly unclear why the result is true, because we should look at a proof of the defective renewal theorem. Like many things, that's a signpost to there aren't really enough people in the class for all of my suggested presentations to take place, but the defective renewal theorem is a nice topic. So you see what we have really is a situation that's, you can probably imagine a very classical problem. You can express it in terms of a light bulb, I think. What is it? You have a sequence of light bulbs in front of you, and then, well, the light bulbs are such that they're either eternal or faulty. So each has a probability P of being an eternal light bulb and shining forever. And then the other ones are called faulty, and then they will only shine for a random amount of time. And that will be according to a certain law. So if I write Z, Z will have the interpretation of, you say at the beginning of time, I'll put my first light bulb in, and then obviously if it shines forever, that's fine, end of story. If it doesn't shine forever, then when it fails, I immediately put the next one in. So I suppose the interpretation of Z is the final time I need to put a light bulb in before I pick one that shines forever. So the kind of interpretation we have is this, where you see the Xi are IID samples of the light bulb law. Well, the faulty light bulb law. Well, I wrote the words the wrong way around, but the faulty light bulb law, okay, that can, whatever, that's new in the application. And then Y is geometric, reflecting the fact that each light bulb has probability P to be eternal. So, yeah. Yeah, well, all right. So then the probability that Y is equal to J is P to the J 1 minus P. So I suppose the probability of being eternal must be this quantity. The eternal probability of that. So P is the probability of 40. So that's the probability, I suppose, of having J 40 light bulbs, you see, because then you have an eternal one after it. So then in that case, we add up the first, J values of the 40 lifetimes to get the final time. Z is the final time at which you had to put in a light bulb. So the point about this theory is that it rarely uses the fact that the law. So yeah, all right. The law of the, that's not quite true. It's the beta I in the application are the things that have the law mu. And then the logarithms of them, let's just define that to be mu, okay, just a notation. So it's actually mu here. So yes, so you see it's here that you have a non-lattice condition. So the assumption is, the hypothesis is that the support of mu has a z-linear span that is dense in the real line, okay? Yeah, so that's the standing assumption of all this. So then what the defective renewal theorem says is the following. It says that I define an exponent kappa, its unique value such that the mean of e to the kappa x, that x is distributed according to mu. X is the 40 lifetime light bulb time. That's 1 over p. Okay, so p is coming up in the geometric definition. That's the geometric random variable. And then you need a further constant. Well, I'm writing it out. I don't seriously expect to be able to interpret it, unfortunately, right now. What we have, though, is we have this degree of smoothness that develops. For the probability, we study the regime and the event that you actually have to wait a really long time for the eternal light bulb. And the probability it's bigger than u is decaying with the usual tilde notation like this. So let's just, before we make any comment about, I don't know, the ideas there or the plausibility of that, in the application, this is a comment about application now, this is equal to, you see mu and nu are related exponentially. So this formula is this. Whereas P, which comes up in the geometric random variable, that is the mean of the subcritical trap Austrian law. So this means that just that kappa is gamma, because the rule that defined kappa is this rule. The rule that defined gamma is this law. So you see, it's a nice problem in a way. in a way, I mentioned you really wanted the last light bulb time to be high. So you have a degree of choice in, there's two levels of randomness somehow in the process of, imagine that the, with probability, with heads, but one thing is that, okay, imagine heads or tails. It's eternal or faulty, okay? And then actually there's kind of two levels of randomness, so that's one decision. So then there's a further coin flip. And then if it is faulty, how long does it last? Well, imagine it lasted either 1 hour or root 2 hours. Okay, so this is done in order to have a non-lattice situation, because you see m plus n root 2 is dense. In the real line, okay? Yeah, all right, well then imagine you have that sort of setup. So at every turn you flip a coin and it's a turn on its head, so that's game over, or it's on to the next waiting period. So then it's a separate coin flip. Is it short or long until we decide again? Is it 1 hour or is it about 83 minutes, whatever it is? Is it root 2 times an hour? Yeah, all right. Okay, so how would you expect, imagine then that you want this thing to run on for about 34 days, okay, really long period. What's going to happen if that happens? So you see, you're obviously going to have to, there's the eternal faulty coin flip, and then there's the short long coin flip. So in terms of the eternal faulty, obviously you're going to have many successes. That's just a given. But then the question that's kind of interesting is to, the unbiased situation is obviously it's just 50% of the time you have a short faulty light bulb, and then 50% of the time you have a long one. But you see, if you condition on, the advantage of having a long one for the conditioning of reaching the 34 days is that it reduces the amount of success you have to have later with the successful avoidance of the eternal light bulb later. So you see, it's sort of an interesting question to think about, how, if you get up to the 34 days, how you're going to do it, because you have these periods that are really quite short, short, long, short, long. The view is you're likely to have more of the long ones than the short ones, because every, you have to pay for everything at some level, but every time you manage to get one of the root 2s in, you've made it slightly less difficult to reach your end. So, well, yeah, I mean, it's a classical problem, and I think this kind of shift of measure that goes on in this formula with this integral is, say, here, you can perhaps try and interpret it. It's sort of like you're trying to turn one measure into another one somehow, to do with things like optimal transport and not unrelated. It could be, I don't always find Feller's treatment, it's in Feller, part 2. I don't always find his discussions, I don't particularly like his style, but anyway, if someone wants to take that a step further in a presentation, that would be helpful. But you see, anyway, if you unfortunately have to perhaps take on trust the statement of the defective renewal theorem to a degree, but you avoid anyway, by the way, with this, perhaps it's also the other idea that it's at this point that the non-lattice condition is really communicating into the topic. Because you see, if you had a different relationship here where it wasn't root 2, but it was 2, then, it would be on the hour that the decisions were being made. After a long time, it would be pretty uniform whether it was 11 o'clock or 12 o'clock you were taking the next decision. You wouldn't be much to distinguish. So there would be a sense of the survival probability for the process having this discrete structure. And it'd be a sense of a geometric random variable. But that would prevent, it would mean that if you look at this statement, U here is tending to infinity in R. It might be the case that with a discrete structure, it would be okay if U tended to infinity in Z. That might be okay with a discrete structure, but here we have the strongest statement that it's true in R. So it's the non-lattice thing that creates the very intuitive sense. The density of this linear span means that there's this kind of washing out of discrete possibilities, and that the different ways of adding the numbers up to get to different little zones is kind of similar with the non-lattice condition, roughly speaking. It was actually the reason that Nina and Alex made a little bit of a mistake, and we joined forces with them on the 4-author paper that dealt with the constant bias tree case, and they'd actually done a preprint in which they claimed that the constant bias case gave rise to the stable limit structure, and that they didn't identify this kind of obstruction. And in a formal sense, the problem was that deep in their 50-page paper, they needed this, and then they were citing a source that said this. That was the origin of the mistake. And you can kind of see what's going on here, because of this discrete picture, that these moments you might have a nice ratio comparison, but these moments you don't have it. It's kind of what's going on. Yeah, okay, so we have a sense then of total time. Maybe I'll just try to say a bit more before finishing. I know it's the end. We have this kind of full deep plus error perspective. So we've just been talking about what's happening from the entrance back to the head, but the total time is to do with entrance back to the head and then perhaps coming back in. So yeah, well, okay, there's this kind of description where this object E has a mean that's an exponential random variable that has a mean, and you want to say at some level that it's dominated by trapped depths, but there's kind of a constant factor correction that comes in that is similar to the, it's the way that you can come up to the top of the trap, move around a bit and fall back in, and you need to take account of that. Yeah, I don't know. I'm in slightly two minds about whether to pursue this. I'm kind of indicating the origin of some of these constants, but perhaps I will come back to this. What I'll probably do is finish for today now, and then I will review my notes and find a way of summarizing fairly quickly the rest of what I want to say about this next time. Yeah, let's stop there.